This video is going to cover section 3.1, part 2. We're going to start on slide number 4 because we finished all the way to slide 3 last week on Friday. We're going to go over some of the characteristics of exponential functions of the form b to the power x. And we did cover some of that last time when we were graphing the two functions on the previous slide, which was 2 to the x. I'm just going to graph it here quickly. You already have it on your paper. So we did establish that the domain, well, maybe I should do that. We do have arrows on both sides. The domain could be any real number, and that is why we use the set notation, integral notation from infinity to negative infinity to positive infinity. And for the range, remember range is the y values, we go from 0 to infinity without including 0. And remember how we talked about how if as f of x approaches negative infinity, so it goes in this direction, not f of x, but x. So as x approaches negative infinity, f of x, the function value or the y values, are going to get closer and closer to 0, but they will not be 0. And instead of that, instead of having an x-intercept, since the function will not touch the x-axis, we do have a thing called the vertical asymptote, and that is a horizontal line, y equals 0. So going back to slide number 4, that is why we do not include 0 as part of the range, and we use parentheses for that. Now we have the graphs of all exponential functions of the form f of x equals b to the x pass through the point 0, 1, because f of 0 or b to the power 0 is equal to 1, right? So it doesn't really matter what the base is because any number raised to the power 0 will be equal to 1. Except, there's one exception here, the base cannot be 0. So that tells me that 0 to the power 0 is actually undefined. And that is why when I tell you almost anything to the power 0 is equal to 1, that will be one exception, 0 to the power 0. That one is undefined. So because we have that point on the y-axis, 0, 1, we refer to that as the y-intercept. And please, it will be really helpful if you get a highlighter, maybe, and you highlight some of the things that I'm circling or underlining, so that when you study, you actually know what to look for. Next, we went over how the base must be greater than 1, meaning the base needs to be positive. And the greater the base, the greater the number of the base, the graph will be up to the right, in other words, increasing. And so the greater the value of b, the steeper they increase. So when the base is greater than 1, it doesn't have to always be greater than 1. It could be less than 1, so that would be number 4. So let me show you an example. So we have here the graph of 2 to the power x. If I want to graph, let's say 3 to the power x, it will have the same y-intercept because 3 to the power 0 is 1. And then 3 to the power 1 is 3. 3 to the power 2 is 9. And then I'm going to go in this direction, but just make sure I don't touch the x-axis. So that will be the graph of 3 to the power x. So now, which one has a greater base? The graph in blue or the graph in red? Red, because 3 is greater than 2, right? So that's what the statement says, that the greater the base, the steeper the increase will be. You might be used to just associating the word steepness with slope, right? And you associate slope with linear functions. But I don't know if you recall from section 1.4, we were taking the slope or the average rate of change of any type of function. And we were using the same formula as the slope. So yes, you can take the slope of any function. Now let's look at number 4, and number 4 says that if the base is less than 1, so we're talking about fractions that are greater than 0. So b is still positive because it's greater than 0, but it's less than 1. So when that happens, the graph is going to go down to the right, or we may say it's a decreasing function. And now in this case, the smaller the value of b, the steeper the decrease. So if we were to graph, let's say 1/2 to the power x and 1/4 to the power x, which one will be steeper? Well, it says the smaller the value.
Oh, 1/4.
1/4. So this one will be steeper. It's a good question for your quiz. Now, number 5 says f of x is equal to b to the power x. It's actually a one-to-one function. You guys remember what that means? One-to-one function. Thank you. It passes the horizontal line test. So yes, it does. So what does that mean in terms of the x and the y values? If it passes the horizontal line test, that means that
X only has one y.
well, that will be the vertical line test. Think the other way.
One to one. You drew it. Y only has y. X only has one. Y versa.
Yeah, something like that. Like, so the definition of a function, for it to pass the vertical line test, we have to say for every x, there is only one y. So to pass the horizontal line test, which by the way, it cannot be a one-to-one function if it's not a function, okay? Remember that test question? Yeah, I got like almost all of you with that question. So for horizontal line test, it tells us that the y's do not repeat. So for every x, there exists a unique y value. Maybe we could say for every y, there exists only one x. So anyways, one-to-one function, there's a one-to-one correspondence. The y values do not repeat. Also, we have here that the graph does not does not touch the x-axis. Instead of that, we do have something called the horizontal asymptote, which is there, and it is on the x-axis, or we may use the equation y equals 0. All right, now we're going to go over the basic transformations that we have studied this since chapter 1, actually since algebra 2. But let's do a quick review. So for exponential functions, we do have all the basic transformations: vertical translation, horizontal translation, reflection, vertical stretching or shrinking, horizontal stretching or shrinking. So let's go over vertical translation first. And for that one, you're going to have a constant either added or subtracted to the y value. And that one is affecting the y value directly, so that's why the graph will move upward or downward. So in this case, what you need to do is either you add or subtract to the y or from y. Let's go over horizontal translation. And for that one, horizontal translation, you will have a constant either being added or subtracted to the x. So it will be with the exponent. That one is affecting the x directly, so it is going to be a horizontal shift. This one is counterintuitive. So if you see a plus, and we're assuming here that C is a positive number. So if you see a plus C, the graph is actually moving to the left. And if you see a minus C, the graph is moving to the right. Remember, it is counterintuitive. So in this case, you subtract, and minus C, you add. And you do that to the X. So please write whatever I'm writing. Like, you need to write it down. You need to. I'm actually considering doing a binder check because I've heard. I'm not going to say from who that you guys don't take notes. All right, now let's go over reflection. We have two types of reflection. If you see a negative that it is outside, and I'm going to give you an example with numbers. Something that might look like this. Why didn't I use parentheses around the negative and the 2?
Because then doesn't that make the exponent negative?
It will not make it exponential. Because if we do something like negative 2 to the power x, depending on if the exponent is odd or even, we're going to be getting positive, negative, positive, negative, positive, negative. So that is why the base cannot be negative. So reflections like that one, they are, the negative must be outside, not inside parentheses. So you have to make sure of that. So that one will make the y values, let's say that you have a positive y value here, and then it turns it into a negative y value. So that would be a reflection across what? The x-axis. So reflection about the x-axis, but what you do is you multiply y by -1. Let's look at the other type of reflection, which is across the y-axis. In that one, you will see a negative with the exponent. Now, if you have an x value here, and then it goes across that, that will be a reflection across the y-axis, right? So it makes sense that the x value turns into its opposite value. So for that reason, you multiply x by -1. And that is a reflection about the y-axis. Now we also have vertical stretching and shrinking. And those, you could notice those by seeing a number that it is multiplying the base, but it's not being raised to that exponent. And let me show you a quick example from the first slide. Here. That number there is like a vertical stretch. You guys notice 42.2 is not being raised to the power x, right? So this is the base, 1.56. That is the exponent. And then 42.2 is just simply the vertical stretch, or the initial value. All right, so those constants will be outside parentheses. And if that number is greater than 1, that means it will be vertically stretching. If the number is less than 1, but still positive, it will be vertically shrinking. In this case, what you do is you multiply the y value by c. Now let's go over horizontal stretching or shrinking. And that one you can distinguish because the constant is going to be multiplying the exponent, like that one. This one is also counterintuitive, so if it is greater than 1, instead of stretching, it's going to shrink horizontally. And if the constant is less than 1, but greater than 0, Gabriel, tell me a constant that is less than 1 but greater than 0. 1/2. Very good. So if that happens, it will be the graph will be stretching horizontally. The reason it is counterintuitive is because you divide instead of multiply. We divide x, by the way. All right, so we're going to graph those two functions. Well, actually four, a total of 4. So I'm going to ask you that you please get a different color pen, pencil, highlighter, something, so that you can distinguish between the both. We have 3 to the power x. And so make sure you do the vertical, the horizontal asymptote. That will be the line y equals 0. And for the transformation, we have g of x is 3 to the power x plus 1. So what type of transformation will that be? You can look at your notes. Emily, what do you think? Horizontal, very good. Jasmine, is it going to move to the left or to the right? You can look at your notes before you answer if you want to. So we say it is counterintuitive. Very nice. So horizontal shift to the left by 1 unit, right? So what we could do, you could do this transformation numerically. So you could consider the y-intercept, which it is the point 0, 1. We could consider this point with the coordinates 1, 3, and then 2, 9. We could use those points as reference. And then what we will do is subtract 1 from every x value. So the graph will be here. Well, the reference points will be shifted like that. All right, now let's graph the next one. So the parent function will be 2 to the power x. Let's not forget about that horizontal asymptote, which will be the line y equals 0. And let me go ahead and write down some reference points. So we have the point 0, 1, 1, 2, 2, 4, and 3, 8. So now, function g, it is a transformation. So, Jonathan, what type of transformation is that?
Vertical shift.
Vertical shift, up or down? Down. So vertical shift, 3 units, down. There's an N. So what that means is we need to subtract 3 from every y value. Or you could just, visually shift every point 3 units down. So this point will be here. 1, 2 will become, what is 2 minus 3? -1. And then what is 4 minus 3? What is 8 minus 3? 5. Now, before I trace my graph, I need to notice something. The horizontal asymptote is also going to be shifted 3 units down. So what is 0 minus 3? -3, right? So we will have the horizontal asymptote for the transformation here. On the exam, you will definitely have to graph an exponential and also a logarithmic function. You can look at the calendar online for an approximate date, but if you need to adjust it, we will. Yes, on my webpage. It will be after we're done covering 3.5. This chapter is very small. We just covered sections 3.1, 3.2, 3.3, 3.4, and 3.5. So it's going to be really quick. 3.5, it's all word problems. Your favorite. Okay, so that is the graph of the transformation. Let's go to the next slide. All right. What we have here is the number E, which it is the second most famous irrational number. That means that we cannot express it as the ratio of 2 integers. That's why it is irrational. Which one is the most famous irrational number? Pi, that's true. What is the third most famous? Square root of 2, nice. Okay, so that number is also called Euler's, yes, or natural number. And so this is an approximation of that number, and this comes in handy when we look at the formulas that we're going to do at the end of the chapter for compound interest and continuous compounding. So if you were to graph this, and I'm going to just make n be equal to x. So if you graph this function, and we say it as x approaches infinity, the function value approaches e. And so if we look at the table of values and we let x equal 1, we will get a function value of 2. When x is equal to 2, the function value will be 2.25. When x is 5, the function value will equal 2.48, and so on. So as the x values or n values get larger, as you're seeing here, what is this number here? 1 million, right? How about this one?
No.
One what?
1 billion.
Yeah, 1 billion. 1 billion. I'm going to tell you an interesting fact. 1 billion in the US is not the same as 1 billion in Mexico. So, in Mexico, 1 billion is a million of a million.
I was told my friends in Greece.
And then here, a billion is 1,000 million. It's good to know, especially if you're going to study like international business. You know, you want to be aware of that. I always thought it was weird. So anyways, so we agree this is 1 billion, right? Yes? Okay. Is it? No, I can't. Yes, 1,000 million. Okay, yes. So as those numbers keep getting larger and larger, the x value here and the x value here, the number will approximate, or the function value, and that's what you see here. It will approximate that number, which is approximately 2.717. 4. Never mind. That's all I know. 2.71.
Okay.
Yes, we do have a poster over there.
3.71.
Wait, you could see?
8, 2.
Are you serious? You can see that? What is the larger n value they have there? Oh, they have 10 million. 10 million. 2.72?
Not super clear, but it's not clear.
Maybe 2.782. That's like a typical approximation for it. However, on your calculator, since you guys are so spoiled, it does have a button for E. Yes, it does. All right, so let's move on to the next slide. So why do we use that number? We use it because it actually repeats a lot in certain exponential functions or logarithmic functions. It is used a lot to predict population growth, bacteria growth, money problems. What else can I think of right now? In chemistry, I mean, it's used so much in chemistry, and I'm not sure in physics. Probably. Okay, so next problem. Now, I'm going to need you guys to get a calculator, please. But we'll read the problem.
In Insatiable Killer. Death's reputation the Great Wolf acquired in the United States in the 19th and early 20th century. Although the label was undeserved, an estimated 2 million wolves were shot, trapped, or poisoned. By 1960, the population was reduced to 800 wolves. Figure 3.6 shows the rebounding population in 2 recovery areas after the Great Wolf was declared an endangered species and received federal protection.
Okay, it is a true fact, and here's the source. So, after the gray wolf, right? After it was declared to be endangered, then the population started growing because people were not able to kill it anymore. So, population, as I might have mentioned before, it grows exponentially. So here is a function that models the population growth. And so what we need to do here is find what will be the population, if the trend continues, what will be the population in the year 2010. So here it's important to consider that f of x is a function where x will be the years after 1978. So x equals 0 represents the year 1978. So I don't want you to say it out loud. I want you to think about how you can find x for the year 2010. Just think for a minute. Write it down. Michelle, what do you think? You what? Well, think about it. Okay.
You subtract 197.1.
Very good. So you subtract to get the difference, and what do you get? 32. Okay, so that means that we need to find the population, or f of 32. So 32 years after 1978. So with your calculator, I want you to find that. F of 32, and that would be 1.26 e to the power 0.247 times 32. Does anyone need help entering that on the calculator? We did a lot of that in Algebra 2. Do you guys remember? Now, the difference with section 3.5, remember I told you it's going to have a lot of word problems, is that we're actually going to be finding the equation that will now be given to us. We're going to find them. We did that in Algebra 2. Yeah, we did.
Yeah, we did.
You did.
Are you going to be working on it during lunch or no?
When?
Thursday.
What do you mean working during lunch?
Like about of the decorations and stuff.
Oh, yeah, I might. Because I'm actually, yeah, I will. Because I have a meeting in the morning, so I'm taking the morning off on Thursday. I was gonna take the whole day since it's my birthday, but I don't want to leave you guys alone.
That's okay, miss. Relax.
I do have more.
Relax.
We will survive.
So,
You trust us.
no, not you guys, like the trick or treating.
Oh.
So then I'm gonna come back at 12. So yeah, during lunch we could do like the last minute and yeah, we really appreciate that. Okay, so I want Lorenzo to give me the answer. Bless you. Bless you. You need a tissue?
No, I'm okay.
Oh yeah.
Well, he's like right here.
Yes, there is a button for E, and it is on the left side of the numbers. So what do you get?
3.42.
Say that again?
3.42 or 3.4.
I don't think so. You enter this.
No.
Well, you have to enter that for the exponent. Mm-hmm.
I know this is very rude to ask, but you're in your 20s, right? Early, no, late 20s or?
I'm gonna be 34.
Okay.
Day past 15 minutes.
She looks depressed.
Oh.
No, you're gonna have.
Believe it or not, I still get carded when I go to certain places.
That's good.
Really?
You still get carded when you
Like ID,
are you proud of that one?
of course. Yeah, you just made my day. So we get 3,412.2. Now, what should we do with that 0.2?
You can't have one too.
That's correct. What if there was a pregnant female
Or
bird?
you can like
No, I'm just kidding. We do round it.
like cut off.
So we round it to 3,412. Okay? All right, let's go to the next slide, guys. And we have here compound interest. Compound interest, we need to copy this definition. So compound interest is interest computed on your original investment as well as on your accumulated interest. So there was another type of interest that you guys probably learned in Algebra 1, and that was called simple interest. Simple interest could be compared to a linear function, and for that one, I is for interest, capital P is for principal, and then you have the rate and you have the time. And so for this one here, this one is not exponential because that one you only earn interest over what you put in at first on the principal, which is the money you deposit or invest. Now, the difference with compound interest is that you earn interest from your original investment, but you also earn interest on your accumulated interest. So you earn interest over the interest over the interest. So here's a little explanation of how that works. So for example, you start with an investment that will be at time equals 0. So your investment is just equal to capital P. And after 1 year, you're going to earn, you're actually earning your principal plus your principal times the rate. So if you factor that, what do these two terms have in common? Here, right? So right here. And if you factor that out, you get 1 plus r. Now, after second year, after one more year, which will be the second year, you are getting that 1 plus r twice. And so if we rewrite that with an exponent, it will be 1 plus r squared. And that's what happens every year. So you keep multiplying by 1 plus r, your principal plus the interest. And so that's why we use then to the power 3, to the power 4, and so on. Now, this will be if the interest is compounded yearly. And that means that n is equal to 1. The number of compounding periods is 1. Now, let's see what happens when the number of compounding periods is more than 1. So if the number of and that means like how many times the interest gets calculated over a year. So if it is yearly, that means the interest is compounded once a year. If it is semi-annually, the interest will be compounded twice. If we divide that into months, it will be every 6 months. For n equals 4, that means quarterly. That means it happens 4 times a year. If you divide it to a year in 12 months by 4, what do you get? 3. So you could say every 3 months. Of course, we have monthly. Monthly is equal to 12, and so that will happen every month. We could also have, and please write this down, weekly, so that will be n is equal to 52. What else do we have? Daily. And that will be n is equal to 365. Interesting fact, in real life, they use 360. I don't know. I'm not an accountant. What else? What if we have something that says every 4 months?
Do this in algebra 2?
Yeah.
Yes, thank you. Thank you. N will equal what? 3.
What do you call them?
All right, so let's go to the next slide so we can, oh, by the way, this is a formula for compound interest right here, where A is the final amount, bless you, P is the principal, R is the rate, and N is the number of compounding periods. And what about T? Time. For problems involving money, time will be in years. If you go to open a bank account or like, let's say a savings annuity or something like that, and you want to sound very smart, you could ask that question. How many times will my interest be compounded for a year? Or what are the number of compounding periods? More than likely, it will be monthly. So let's go to the next slide. Here is a way to derive the next formula that we're going to look at, and that will be the one for continuous compounding.
What's that? Or
Continuous compounding. And for this formula, do you guys remember what we went over here, right? So I did change the n for x's, but let's go back to n's. And so does this formula look a little familiar? Yes, right? It kind of looks like the one from the compound interest. The 1 plus 1 over r and blah, blah, blah. So the way the formula for continuous compounding gets derived is you increase the number of compounding periods. So you may say n is approaching infinity. It's getting bigger and bigger and bigger. So if you do that, and then you could use arrow notation, you could graph it to see it, you could use limits, you could see that this value here that one is going to approach infinity. And so if we go back to that other formula, this one here, on that other slide it was written this way. So as n got bigger, in this case they're using h, we know that this was approaching e, correct? Yes? And so that is what we have here, the formula for continuous compounding. If I had more time, I will derive it, but I really don't. I really want to start with 3.2, at least start it. Okay, so let's go ahead and answer that question. And here we'll have it's one problem, but we're talking about two different accounts. So Ezekiel, please read the problem.
You decide to invest $8,000 for 6 years, and you have a choice between two accounts. The first pays 7% per year compounded monthly, and the second pays 6.85% per year. Compound continues.
All right, wait. Give me a second. So let's talk about the first account, $8,000. The time is 6 years, and then the number of compounding periods is 12, right? And the rate is 7%. However, we need to use decimals. Should it be 0.7? 0.07. All right, and we're going to use this formula. 8,000 times 1 plus the rate, which is 0.07, over 12 to the power 12 times 6. So it's this formula here. Yeah, it's multiplying here. Okay, now the other problem, the second account, so go ahead and keep reading, Ezekiel, a little slower, please.
Oh, the second one?
Yeah.
The second pays 6.85% per year. Compound continuously, which is a better investment.
Okay. So the rate is 6.85, so that will be 0.0685. The time, since we're comparing them, I'm going to use the same time, so 6 years. We're talking about the same amount of money, so $8,000. And then, what else do we need here? That's it. That's all we need. So we will use this formula. If we do our substitutions, we will have 8,000 times e to the power 0.0685 times 6. Okay, so I want this side of the room to answer the question about the monthly, compounded monthly. And then you guys here will solve the question about the continuous compounding. You may use your calculator. You have it already? Okay, who's ready? Gabriel, you got it? Samantha, you have yours? Come on, guys. You need to try on the calculator so that we can agree on one answer. Yes, Gabriel? What do you get? 12,000? 0.66?
Yes.
Point
6.
6. So let's say 60%. Okay, and then Jonathan.
12,160.
12,000, what else?
160 cents.
Do you guys agree?
Yeah.
Yes. Okay. So which one is a better investment?
The one compounded.
This one, actually, the first one, right? But what if the interest rate was the same? Let's make the interest rate 0.7 or 7%. So right here, I want you guys to try the same problem, but with 0.07.
Way more.
Like how much more?
It's 12,175.70 cents.
Say that again?
12,175 and
175.70 cents. Okay, so if we were to compare continuous compounding with compounded monthly at the same rate, then we will go for the continuous compounding, right? All right. So this is the end of the video for section 3.1, part 2.